Section 2.2, polynomial functions of higher degree. First definition here is a multiplicity. You will see this word used throughout this section. Multiplicity tells you how many times a particular value is a solution to an equation. So if x equals 2 has a multiplicity of 2, it means that it is a solution twice to a particular equation. If x equals -5 has a multiplicity of 3, it means it's a solution 3 times, and so on. An example of this would be the polynomial x squared minus 6x plus 9. If we solve this by factoring, our two factors are x minus 3 times x minus 3. Set each of those factors equal to 0, and they're both going to produce that same solution of 3. So we would say our solution of 3 has a multiplicity of 2 because it is a solution to this equation twice. So when you see that, you know what the book is referring to when it talks about multiplicity. First part of this section, again, is going to be an overview of how you can get a quick idea of how graphs look. Just like the transformations we talked about in Chapter 1, it's designed to give you a quick picture of something, not necessarily an accurate, precise graph each time. The leading coefficient test is used to determine how far right and far left behavior is of a graph. If our polynomial has an odd exponent with a positive lead coefficient, so that could be something like y equals x cubed. The leading coefficient test is going to tell us how the extreme left-hand portion and the extreme right portion of our graph behave. When it is an odd exponent with a positive lead coefficient, far left of our graph will always fall. The far right of our graph will always rise. So any function with an odd exponent and a positive lead coefficient for its leading term will always fall left and rise to the right. What goes on in the middle here, we're not concerned with right now. We're only concerned in what does our graph look like all the way on the left and all the way on the right. If there is an odd exponent with a negative lead coefficient, something like this, now those are obviously going to be reversed. It's going to rise to the left, fall to the right. Again, what's going on here in the middle, we don't know for sure. We're not too concerned with at this point, but we know any graph that has an odd exponent with a negative lead coefficient will rise left and fall right. So those two left and right behaviors take care of any polynomial whose leading term has an odd exponent and a negative or positive lead coefficient. Likewise, we can do the same thing for even exponent graphs. Most well-known even exponent graph we have is our parabola. If our lead coefficient is positive, we know our parabola opens up, which means it's going to rise left and rise right. Again, depending on the degree, it could be doing whatever in here. We're not concerned with that. But any even exponent, positive lead coefficient, will rise left and rise right. It's an even exponent with a negative lead coefficient, something like this. We know that parabola opens down. Our left and our right behavior then is such. Depending on the degree, we don't know for sure what it's doing in here, but all even exponent, negative lead coefficient will fall to the left and fall to the right. And that's all the leading coefficient test is going to do, is tell us what is going on in the far left extreme values, the far right extreme values of our graph. So looking at these, determine the left and right behavior of each function. The only thing we need to look at is the highest degree term. So I'm only looking at this negative x cubed. It is an odd exponent with a negative lead coefficient, odd exponent, negative lead coefficient, all behave the same as what this graph does here. So it's going to rise left and fall right. Next one, f of x equals x to the fourth minus 5x squared plus 4. Again, we're only looking at the highest degree term. Nothing else in the function controls the left and right behavior. So when I look at this one, we have an even exponent with a positive lead coefficient. Even exponent with positive lead coefficient tells us that it rises left and rises right. The third one, again, we're looking at the highest degree term only. We have an odd exponent with a positive lead coefficient. Odd exponent, positive lead coefficient, falls left, rises right. And that's all that the leading coefficient test does for us, is determines that left and right behavior. We can combine this, though, in conjunction with things we already know how to do as far as finding solutions or real solutions to an equation. Combine that with what we now know about the leading coefficient test and get reasonably good sketches of graphs, not exact sketches, but not too poor as far as what we're going to know about the graphs. So find all real zeros of each function and sketch the graph of a function. Remember, real zeros correlate to x-intercepts when we look at graphs. So if I want to find the real zeros of this, x-intercepts is the same thing as putting in 0 for y. On the right side here, we could factor an x out right away. Continue factoring. Factor this trinomial, x minus 2 times x plus 1. Set each of those factors equal to 0, and we get x equals 0, 2, and negative 1. So now on our graph, we know that there are 3 x-intercepts at negative 1, at 0, and at 2. We also know that those are our only x-intercepts because we just found the only ones that are possible. So now if I combine this with what we know about our leading coefficient test, looking only at that first term, odd exponent, positive lead coefficient, we know our graph has to fall left and rise right. Which means if I take that according to these x-intercepts, if this x-intercept of negative 1 is the last point that crosses the x-axis, I know when it crosses there that it has to be falling to the left. Likewise, on the right, if this is our last x-intercept here at 2, when it crosses that point, it has to be rising to the right. What does it do in the middle here? Well, I know it has to come up through this point, back down through this point, and back up through that point. So the only thing that isn't accurate here in our graph is the dotted portions in the middle. We know that this goes up here between negative 1 and 0. We don't know how high. We know it comes back down through 0, and we don't know how low it gets here between 0 and 2, but we know that that is going to be the general shape of our graph, and that's all that we are concerned about in this section. Letter B. Again, put 0 in for y. Real zeros are the same as x-intercepts. We can pull out, in this case, a x squared as well as a 2. So let's pull out 2x squared. That's going to leave us with negative x squared plus 1. Set each factor equal to 0. We get 0 and plus or minus 1. Those are our two solutions. Now, this is where you need to be careful. We know that the degree of a polynomial tells us how many total solutions that polynomial will have. In this case, we had a degree 4 polynomial, and we found 1, 2, 3 solutions. We know there are 4 total solutions, however. Some of them could be imaginary. In this case, they're not. Okay, or some could have a multiplicity of more than 1, meaning they are a solution more than once. In this case, how many solutions do we expect to get from this factor that is degree 2? We expect to get 2. We only get 1. Anytime an even powered factor produces less solutions than it should, then we are going to have what is called a double root, meaning that it is going to correspond to a touch point when we look at the graph. And we'll show that here in a second. So only when an even powered factor produces less solutions than it should, there is a touch point on the graph. So when we go to plot these intercepts at -1, at 0, and at +1, let's check out our left and right behavior. Again, for that, we only look at the first term there. Even powered factor, negative lead coefficient. We know that that falls left and is going to fall to the right. So that means through these last intercepts on the left and the right, our graph has to be going that direction. Now we also know that this solution of 0 is going to create a touch point on our graph. What that means is that's an intercept in which the graph touches and turns right back in the other direction. It does not cross at that intercept. So at 1 and -1, it is going to cross. Then it's going to come down at 0, touch, go right back up, and back down through here. So anytime we have a touch point, it just means that it does not cross at that x-intercept. It simply touches at that x-intercept and goes right back in the direction that it came from. Letter C. Find our solutions first. Okay, this is a situation where once I plug in 0 here, that's not the easiest equation to solve in the form that it's in. Let's get rid of the fractions by multiplying everything by 4 here. And actually, so that leading term is positive. Make it easier to factor. Let's multiply by a -4. So we get 0 equals x to the 5th minus 3x cubed minus 4x. So when we continue factoring this, first thing we notice is that we can pull out a greatest common factor, which is going to be an x, leaves us with x to the 4th minus 3x squared minus 4. Continue factoring. What multiplies to be -4 and adds to be -3, that's -4 and +1. So we're going to have x squared minus 4 times x squared plus 1. Set each of these factors equal to 0. We get x equals 0. X squared minus 4 equals 0. X squared plus 1 equals 0. We get plus or minus 2. Here we get x squared equals -1. Go to take the square root of that. That is not real. So we have 3 real solutions to this equation. Let's plot those x-intercepts. We have 0 plus or minus 2. Look at our right and left-hand behavior. We're just looking again at that first term. We have an odd exponent. We have a negative lead coefficient. Odd exponent with a negative lead coefficient tells us that this graph is going to rise left and fall right. So through this point on the left, we need to be rising. Through this point on the right, we need to be falling. All of these intercepts are going to be crosses because we did not have an even powered factor that produced less solutions than it should. So we're going to cross here, and cross here. Number 3, find the real zeros first. Putting 0 in here and looking at this polynomial, first of all, we can divide everything in here by 5 to make this a little simpler for us to work with. That leaves us with 0 equals x squared minus 2x minus 1. This is not factorable. Since it is not factorable, we need to go and use the quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Simplify, we get 2 plus or minus underneath the radical. That becomes 4 plus 4, which is 8. 2 plus or minus 2 root 2 all over 2. Factor 2 out of everything and cancel. We're left with 1 plus or minus root 2. So there's our two real zeros. Right and left behavior. Looking at this first term, even power. Positive lead coefficient. This graph is going to rise left and rise right. Plug 1 plus root 2 into your calculator. 1 plus root 2, you get a little bit more than 2, between 2 and 3 here. 1 minus root 2, you get about negative a half. This graph's got to rise left, rises right. We don't know how low it comes down here, but again, we're not interested in that at this point. Last one here. Plug in 0 again for y. Notice once again we can divide everything by 5, so the numbers are a little bit easier to work with. Leaves us with x to the 4th plus 3x squared plus 2. This is factorable. X squared plus 2, x squared plus 1. Set each of those factors equal to 0. And solve. First one is not going to be real. Second one is not going to be real. So none of these solutions are real solutions. Remember, real solutions correspond to x-intercepts. So we know this graph is going to have no x-intercepts. Right and left-hand behavior. Looking at the first term, even exponent, positive lead coefficient, tells us our graph is going to rise to the left and rise to the right. There are no real solutions, which means there are no x-intercepts. So how can we have a graph that rises to the left and rises to the right but never crosses the x-axis? Well, that means our graph has to be contained totally in quadrants 1 and 2. Rising to the left, rising to the right. We don't know what's going on in here, but we do know that it does not cross the x-axis, so everything has to be up in quadrants 1 and 2.